Advanced Operating Systems 2020, Term 2, Week 5, Microkernel Design and Implementation. Okay, so today is about how to get microkernels right, and that basically means L4 microkernels, because they're the ones built right. They've been sort of successful over the years. These are some of the systems where L4 microkernels are deployed. The one in the 350 is not ours. It's a clone of ours that was done years ago. But for example, anyone who's got an iPhone has one of our earlier kernels running in on the secure enclave. And there is a whole bunch of other projects. Oh yeah, the trains is not ours either. That's a different one again. Yet. It's coming. And it's definitely getting into more and more products, yes. So the whole L4 thing started about a quarter century ago. So it's a really long time. Which means it's almost as old as Linux, and that's ancient now. And it all goes back to this guy, Jochen Liedtke. You've seen this picture before, and also you've seen this definition of what makes a microkernel, which is the minimality principle, right? Stuff should only be in the kernel if it has to be in the kernel in order to provide the right functionality and security. And if not, then it should be outside. And that really is the basis of the flexibility that microkernels give you. And as I said earlier, we had 25 years history of research and development in microkernels. All of these started off as research projects, and then most of them went into actual deployment. So this is the stuff that's flying on the 380s, which was a clone of an earlier kernel of ours. And Fiasco is in a number of products. This is the thing that's on the iOS devices, and then there's seL4, of course. So one of the interesting things is just before L4 was done, John Osterhout, a professor from Stanford, had this paper at a workshop that says, why are operating systems not getting faster as hardware does? And he had this nice table which showed that over 10 years or so, the basic core operating system performance as measured by the null system call was pretty much constant, while hardware increased massively in speed. And turns out, well, seL4, or the original L4, started off being much faster already, but what you can see here is it's basically kept track with increasing hardware speed. So the null system call measured in numbers of cycles, so that scales with clock rate obviously, fluctuated up and down, but that's mostly a reflection of the hardware. But roughly it stayed the same, all of a few hundred cycles. And it basically means at the limit of what the hardware can do. The one real sore thumb sticking out here is the Pentium 4, the net burst architecture. That was the absolute nightmare of a computer architecture, the worst ever built, which was just massively speculative, and there was so much stuff in flight that when you trapped in the kernel, it would take of the order of 500 cycles just to resynchronize all that stuff and give you control. I mean, imagine that, just a trap. 500 or something cycles, or 700 or whatever. And so to do a complete context switch, 2 kilocycles, really awful. The other end is the Itanium, which unfortunately is pretty dead by now. That was a real designed architecture that was really designed to make context switching fast. And we could do an L4 IPC in 36 cycles, and we knew we threw 2 cycles away, so the theoretical limit was 34, but it was close enough. And in general, the trend is, yes, it's basically scaling with the clock rates by having roughly a constant number of cycles. And of course, that means in terms of absolute latency, it's gone much faster over the years. The other interesting statistics is, and this comes back to the real essence of a microkernel. If you look at any sort of software artifact, that's been around for decades, what happens with it? No matter whether it's Windows or Linux or Office or MySQL or Apache, what happens to those things? They get bigger and bigger, right? Things explode. And in contrast, this is what happened to L4 microkernels. The very first one was written all in assembler. 6,000 lines, so this probably corresponds to about 4,000 lines of C, roughly. All the others were bigger, but I mean, this was basically, every line was hand optimized there, and so including a lot of stuff that didn't really merit this kind of optimization, so it was a bit over the top. seL4 is about a factor of 2 bigger, but this is actually a number that's in a way bloated because the way seL4 was developed, and I'll talk about that in week 8, I think. The original seL4 was speed coded in Haskell and then manually translated into C. And there's some code bloat from that. Basically in Haskell you write lots of small functions, and so there's more modularity in a way than you would really need. So it is a bit bloated. And could be written much tighter, but it's not worth it. But the basic story is, even though this kernel is way more powerful than that one in many ways, it's kept the size more or less. And there are some interesting lessons there. So what I'm going to do is pick on part of what we learned in this period. So in the first week, I talked about the first and second generation microkernels. So the first generation was Mach and things like that didn't perform, and it was impossible to build anything sensible on them. And then 2G, second generation microkernels, that's represented by the original L4, 25 years ago. And this was the one that showed, yes, performance is not an inherent limitation. We can make those things fast. And it was demonstrated with this SOSP paper in '97, where they did a Linux port to L4 and showed that, well, yes, it's about 5% performance degradation, something compared to what the Mach people did, where the performance degradation of their Unix port to their kernel was massive. But there is a number of problems that were unresolved, and some of them it took us a long time to deal with. So there's some of them, and I'll go through all those with some examples on what the issue was and how it was resolved. And the last one of these we only resolved last year. So it took us well over 20 years to actually get to the bottom of a neat solution for this one. But I really believe this is now knocked out as well. Okay, so what are those issues? The one is no delegation of authority, which really made it difficult to build general security policies in those systems without massively losing performance. This is obviously solved by capabilities, right? With capabilities, we have a well-defined authority delegation model. If you have a capability, you have a grant right on an endpoint, then you can transfer a copy of the capability to someone else, and that's an authority delegation. And this, for example, allows us to have subsystems that run with restricted resources totally autonomously. The example I went through with the memory management model, where you can partition memory and then just hand over to one partition capabilities to some untyped, and it can manage that memory totally autonomously without ever calling back. That wasn't possible in the early kernels. Okay, so the second one was interesting in the kernel. The original L4 kernel had sort of an interesting memory management model where there was a notion of delegating memory management to a degree to user land, but it was only ever implemented in the very first kernel, and it was still very limited. And there was basically no real resource isolation that prevented denial of service attacks. So in that sense, you can say the original L4 was just as broken as any mainstream operating systems these days, whether it's Windows or Linux or so. None of them have a proper resource isolation mechanism that really completely isolates things. And in seL4, we finally done that. And so one of the examples of how this is exposed in the original model, it has this conceptually core model of recursive address spaces. So a mapping is always from page to page. And if you have a page, that implies the right to map it onto someone else. So you can send a page mapping by IPC. And there was two fundamental operations, map, where if you have a page that's mapped, so it has a mapping to a frame in memory, then you can hand a copy of that mapping to someone else, meaning they get a mapping to the same physical frame. So this is how you establish shared memory. And so there was the map operation, and then there was the grant operation, which is sort of not the copy, but the move. So you transfer your own virtual page to someone else, and you lose your mapping. And these are general mechanisms with which you can do all memory management in principle. And the unmap you can undo, the grant you can't, because then you lost the thing. And the fundamental conceptually neat model is mappings are from page to page, from virtual page to virtual page. And of course you need something to bottom this out. And there was this magic initial address space called sigma 0, which was an identical map of physical memory. So all the memory the kernel didn't use itself, it mapped into the initial task one-on-one, and then the task had these virtual pages that corresponded to frames, and it could use those operations to manage memory. Does anyone see the problem with this model? At the very least, it consumes some space in a page table, and if that space is not there, then a new page table needs to be allocated, right? So, and if you do this mapping sparsely, like one per super page basically, then each mapping will require creation of a new page table page. So it consumes resources, right? And there's no way the issue of this is charged for it, because all they have is a page, and they send the page via IPC to a receiver to get that mapped into the address space. So basically by this operation you implicitly consume kernel resources, and there's no model behind for managing that cleanly. And this was fundamentally the breakage with this model. And the other was that the mapping database, because these things are revocable, there's a complex mapping database behind that's expensive to maintain. But this is the real main thing, right? You basically have a way, if you have, particularly in a 64-bit machine, if you have a bunch of pages and you have somebody, a different process, then you basically can mount a denial of service attack against the kernel by each one mapping you only need one page for it, right? Each one mapping the same page forward and back all the time, and whoop, you consume all the memory with page tables. Okay, so that's bad. And of course, in seL4 we replace that by our user, by the model where the user will have to explicit provide memory to the kernel for its metadata. And as a side effect, we get rid of the magic of this initial address space. Magic is always, anything that's magic usually has its bad side effects. Okay, so this takes care of the kernel resource management issue by our new memory management model. And as I said earlier, in terms of operating systems concepts, this was the main innovation in seL4, and was actually Kev's doing. He's been working on that one for probably somewhere between 5 and 10 years to work out the proper model for doing this. It's a typical thing. Once you have the model, it seems obvious and simple, but it's a long and arduous way to get there. And the second one, the other two, these two are actually closely connected. The one is that we have covert channels, because, and I'll talk about, well, I might as well talk about it. So there's a covert channel issue and the encapsulation issue. So if you have a message passing system, you need to address your messages somewhere, right? You need to send it to denote the destination where the message is going. And of course, in seL4, we have these endpoints for doing that. In the original L4, they used the receiver thread ID as the destination. So the thread IDs were global names in a global thread ID namespace, and you addressed an IPC to such a global thread name. And so this is easy in a way, and it guarantees you authentication because the kernel, when delivering the message, the receiver will deliver the sender's unique ID with this, and the receiver knows where it's coming from. And of course, the seL4 model is to have a port-like intermediary where you send to a port, you receive from a port. You sort of lose this authentication issue, which is a good and a bad thing. It allows you to have really anonymous services, which are in a way good for security, and you can force the authentication back by what? What's our mechanism in seL4 for identifying senders? Badges, yeah, okay, right. So the badge doesn't directly identify the actual sender, it identifies that someone has a valid right to use this, and it allows you to distinguish between, say, it has a real advantage of identifying basically the owner as the logical owner, which is in address space, rather than the thread, which is sort of irrelevant for any other party. And that's actually an interesting concept in itself. So one of the issues that existed with addressing IPC to threads is, imagine you have this multi-threaded server where it has basically it has a thread pool for servicing requests, and does its load balancing or supposed to do its load balancing. The problem is, since your IPC, your requests get addressed to individual threads, this basically means the client has to do the load balancing, which is not a very good model, right? Because the client has no clue who's loaded and who's not. So that's the wrong model for sure. So what do you do? How do you take this obligation to load balancing the server off the client? There's an obvious. Hey? Queue? Well, you need to have a receiver, right, of some sort. The client sends a message to a specific thread. So what do you do?
Queue the server on the endpoint.
Well, you have a load balancer gateway thread, right? You send a message to a gateway thread, and the gateway thread then forwards it to individual worker threads. And that way it remains transparent to the client. The client only sees the gateway thread, and this one load balances. What's the drawback of this?
Is that like a bottleneck?
Presumably not, because this one just forwards IPCs. And the way it balances between those, it could use any mechanism, right? It could use spin locks or whatever. It obviously needs some sort of locking to make sure requests don't get lost or duplicated, but it's the assumption is that the actual work that needs to be done is much more heavyweight than just receiving the message, so it shouldn't be a bottleneck. Now the problem is then, okay, the client forwards the request to one of these workers, and then the worker eventually is done and tries to reply back to the client. But this is not how this call type message passing works, right? Call means I do the context switch to this one and then switch back. So the reply has to come from this guy rather than from that guy. It won't, the normal call type RPC operation doesn't support this. So they played around with various ways of doing this, so including support for limited masquerading, where the sender could reply pretending it's this one, which is safe because they're all from the same address space. But that's a complication. If you don't do that, then you need to duplicate everything, which of course is bad. And of course, another problem with this is you can't interpose. So assume you have communicating processes and you want to put a security monitor in between. if IPC is addressed to thread IDs, then you can't easily do that. And again, this functionality was desired, so they went through a number of hoops to try to make something like that working, and it all just made things way more complicated. Obviously, with capabilities and endpoints, all this complication goes away because you send to an endpoint, any of the workers can pick up the message from the endpoint, so load balancing is trivial, and then they just reply back through the reply endpoint, so all easy. So that's been sorted, and so having the intermediate as the endpoint removes the need for having this global space of thread IDs, and that's what introduces covert channels. Whenever you have global names, you have covert channels because you can signal by having something available or not available. The encapsulation goes away with endpoint as well. The final really big issues is what, as I said, what took us the longest time, and I'll cover that a bit later. Before I get to that, I want to talk through a few other things. So there was actually a whole bunch of design and implementation tricks about the original L4. There's two SOSP papers. One basically talks about the design and the other about the implementations. And there's a lot of interesting stuff, and most of them we discarded meanwhile. One of these features was long IPC. So in the original L4, IPC was a true message passing operation. You sent data, including arbitrary length strings. They didn't even have to be aligned. So you could do an arbitrary buffer somewhere in your memory. You could send that to a receiver, to a location of the receiver's choice, obviously. So the receiver said, I'm willing to receive a long message, and this is where it should go. And then the kernel would do the copying. So what can go wrong? This can trigger page faults, because just because this guy says there's a string here doesn't mean it's actually mapped. And so when the kernel copies, it needs to worry about page faults. Now this is pretty ugly because you're handling a system call. So the user trapped into the kernel, you're in exception mode handling a system call, and now you may run into page faults. So what do you do?
So the kernel fault goes into the...
Yeah, so there's really two ways you can do this, right? Either you have to pre-check all those buffers, whether they're mapped, and this basically means the kernel has to traverse the page tables, so that's expensive. Or you do the optimistic way, she'll be right, but then you cop a nested exception, right? While in the kernel, you cop an exception. And what's the implication of that? Yeah. By its own, that's not a particular tricky thing, right? It's like nested interrupts. You can do that. But what's the problem? So you're operating in the kernel, which means you have a notion of a caller of the system call, and you have then a destination. You massage both of these thread control blocks, and then you go busy and do some copying. And while you're doing that, you suddenly copy an exception. So the kernel code execution gets diverted into an exception handler. And the exception handler somehow has to fix this up. Now you're in a sort of incomplete state while doing this copying, and now you get concurrent access to the same state, because whatever the exception handler does, it will need to refer either or both of these threads as well. So you get into concurrency control issues in the kernel. You have to make sure that everything is concurrency safe, or at least in a controlled way, because you know when these exceptions can happen and when not, so it's not completely open slather, but it just increases the complexity of the kernel significantly. And the code for doing this long IPC was actually pretty messy. It was, even in the first kernel we built here, which was Kev Smith's kernel, it was written in C, but it was like hundreds of lines of C just for getting this copying right. Because what happens, of course, when a page fault happens, what happens in an L4 thread when a page fault happens, when it triggers an unmapped address? No. You're dealing with this, right? The user level page fault handler gets invoked, right? So depending on whether the fault happens in the source or the destination, this one's page fault handler or that one's page fault handler needs to get invoked. And so how to do that? The kernel needs to do an up call into the page fault handler, needs to pickle up all the state so it can return when the page fault handler has mapped the page, etc. So imagine there's a shitload of bookkeeping you need to do that's extremely easy to get wrong. As anything to do with concurrency, right? Concurrency is always easy to get wrong. So, and of course, this is not minimal. Why does the kernel have this copying, right? If you want to copy bulk data from a sender to a receiver, why does the kernel have to do that? You can just have a trusted intermediary who does the copying. It's trusted code anyway. So if you want this functionality, you just have a server thread that has access to both address spaces where you can request to do the copying. You don't need the kernel for that. So this was a really very un-microkernel-ish optimization. And we definitely dumped that one in seL4 for good reason. Fiasco kernel, I think, still has it. I don't understand why. So another thing we had was timeouts. So the idea here is you have two processes that communicate via IPC. So one does a send, the other does a wait. And the kernel then copies the messages in between. The point is these things should be mutually distrusting, right? You shouldn't have to trust that the other side plays balls. And of course, that means if you're here waiting for someone to send something, they may never do it. And you basically can DOS someone by not replying to their IPC messages. For example, the client sends to a server, the server responds, and the client, instead of being ready to receive the message, just goes away to something else, and the server is blocked. So that's a bad situation. In order to avoid that, any IPC operation in the original L4 had a timeout value, and blocking was limited to the timeout, and if the timeout expired, then the IPC would be aborted, and you get an error code. That's all fine. Of course, you need those timeouts not only on the IPC message itself, but if you have long IPC, then it also needs to be done on any invocation of, say, page fault handlers while this IPC is happening, etc. So in the end, an IPC had four timeout values associated with it. They had a nice property you could do. There was a special magic to receiving from a non-existing thread, which was basically a blocked wait, a timed wait. But again, you can have a timer service. You don't need a kernel for that one. The real reason why this one, there was sort of a good motivation behind it, that you want to be able to stop someone from blocking you indefinitely. The problem is there's really no sensible way to determine these timeout values. The only place where they're really useful is in networks, because they interact physically, right? There's signals traveling across the wire, and you have a notion of what's a sensible timeout value. Obviously, modulo factor of 2 or 4 also doesn't really matter, but in networks we have sort of really natural ways of defining timeouts. In most other things, certainly not as long as you're not dealing with physical devices, there's no sensible way of determining these timeouts. And in the end, everyone used either 0 or infinity. And of course, you only need the 1 bit to represent those. You don't need a floating point value for timeouts that range from milliseconds to hours or days. So we abandoned this, and really replace them by two values. Most IPCs don't have a timeout. Some have. Optionally, you have a non-blocking version of some operations. So you have a non-blocking send, for example. But they're really needed because, as I told you, you shouldn't use send only or receive only IPC, right? They're only usable for either dealing with exceptions or initializing things. In particular, for what is mostly used, which is the call on the client side and the reply wait on the server side, you don't need it because of the particular semantics of the seL4 call IPC, where it creates this reply endpoint, which then the server replies to, and the server is basically guaranteed to be able to send to this reply wait point, and it can't be blocked. And if this client goes away, well, then the reply endpoint goes away, and the reply fails, but it doesn't block the server. So for the normal case where the client trusts the server, but the server doesn't trust the client, you don't need to do anything. The semantics come out right. And if the client doesn't really want to trust the server, then there should be, but presently isn't, a variant of call that will fail if the server isn't ready, because that's not the normal situation, right? This server should be running at higher priority, so the fact that you're executing means the server should be blocked waiting for reply, so the call should immediately go through. And if it doesn't, there's something wrong. So there's an argument for having a non-blocking call operation. Anything in L4 kernels traditionally is really optimized for performance, and that set them apart from the beginning. And one is really sort of the whole core of L4 kernels is this fast message passing, and it is designed to be executable really quickly. And this is an example of the fast pass. So the way it's constructed is the execution path, that's the normal one that needs to be fast, is coded very efficiently, and at the beginning, that's actually not included here, that's sort of in the prologue. The first thing it does is, are the conditions satisfied for doing the fast path? And if so, then run through quickly. And what it needs to do is obviously save some state, look up the capability, because the caller supplies a capability for an endpoint. You need to know whether that's a valid cap. Get the endpoint, check whether anything is queued on the endpoint, so is the receiver clocked on the endpoint, then just deliver, and that's part of the fast path. So from the endpoint you get a reference to this receiver's thread control block, check whether it's runnable as soon as it gets the message, do a priority check, and then from then on we know we just need to switch to the receiver. We then block the caller on the reply object so we can return back to it and transfer the scheduling context. And then do the context switch. And the context switch, of course, part of this is this fast message delivery where in-register messages don't need to be copied, so they're just left in place and then restored date. So all this can be encoded in of the order of 100 instructions, and that makes it really fast. The important point to note is an seL4 IPC is always done from the sender's context to the receiver's context. And that allows you to do this zero copy register data transfer. So very, very simple, straightforward code. And what's in here is, in particular, you don't see an invocation of a scheduler. You don't see any checking of time slices or anything. This is intentionally optimized away, and I'll explain that in a few slides down. So we don't invoke the scheduler, and we don't give the receiver a new time slice. So the receiver executes on the sender's existing time slice, and so that we don't need any queue manipulations, nothing. So that was what's make it fast, but there's some implications from that. So this is the code how we decide whether we're in the fast path. It basically collects all the conditions in a Boolean and then just does a conditional jump to the slow path. And this means there's only one conditional branch in the whole thing. Everything else is Boolean operations. And that means minimizing mispredicts this branch will be predicted as being not taken if it's going forward. And so we make best use of the branch predictor. On ARM we can make use of the instruction predication, which basically means this can be done on an ARM without a jump by just setting this predicate. So I don't think the latest, the V8 architecture has this anymore, but prior to every instruction on an ARM had predication bits, which means every instruction could be executed conditionally. And this is a way to do this branch in a way that where you don't even need a branch. You don't need speculation on whether the branch gets taken, but you still need a branch predictor. Okay, so L4 kernels from the beginning were designed to be suitable for real-time use. And yesterday I talked a bit about what's required for supporting real-time systems. And turns out, well, they sort of had a lot of it, but not everything. But one of the things that all the L4 kernels, or most of the L4 kernels had in order to get average case performance maximized was running with interrupts disabled. So the kernel, we trap in the kernel, hardware disables interrupts, and most operating systems will then just do some minimum safe state saving and re-enable interrupts and then continue and be interruptible, and then you have turn interrupts on and off while you're executing to make sure you don't get interrupted in critical sections. That's how example Linux operates. So, and that's why when I talked about virtualization, turning on and off interrupts, how it happens a lot in kernels like Linux. In L4 kernels, traditionally not at all. So this is good for average case performance because you don't have to worry about any concurrency control in a single core kernel because you know there's no concurrent accesses. You don't get an interrupt until you're out of the kernel, and that makes it way easier to reason about the correctness. And obviously it also helps average case performance because any critical section, any locking always costs, even if it's not contended. What's the drawback? Obviously it limits interrupt latency, right? You can't take an interrupt while in the kernel. And if you have long-running operations, then interrupts may be disabled for a long time, and that's not good for real time. So if you look at any sort of commercial protected mode real-time operating systems, of which there are a few around, QNX, Green Hills, Integrity, Pygos, there's a few, there are inevitably microkernels of sorts. What they typically do is being pretty much fully preemptible. So they do what I said, minimum state saving, turn interrupts back on, so they get minimum interrupt latencies. To me, this is a disastrous mistake. Why do I say this? I sort of gave the answer a few minutes back. Remember, these are systems meant to be used in really safety critical systems like aircraft, etc. So, added complexity, yeah, because you have lots of concurrency control in the kernel, right? You have all these critical sections to deal with, and as I said over and over, and everyone you should understand, concurrency is very easy to get wrong. And usually you do get it wrong unless you prove it right. And none of these are proven right. So this is extremely dangerous. And it's also the limit of this, it's actually limited to what it can buy you, because if you think about in the fast path IPC I showed you, there's no point enabling interrupts because the time through this, the latency of executing that code is less than actually invoking an interrupt handler and starting to find out what the hell you're doing. So this would be code you wouldn't want to be preempted anyway. How about the scheduler, which is actually one of the longer running operations? You can't really preempt the scheduler, right? Because the whole point of an interrupt is to schedule something else. Now, when you're in the middle of a scheduling decision, that's sort of pointless thing to do, right? The schedule needs to run uninterrupted. And that's already two important operations, the two most important operations you do, you don't want these interrupted. And of course, that means anything you potentially would want to be interruptible has a longer latency than an L4 IPC already. So it's really a few longer running operations, and seL4 is designed to minimize those. If you look at the sort of system calls you're using, which ones might be long running? And with this I mean, say, at least an order of magnitude longer than a fast IPC. There's sort of some medium weight operations that typically mapping, because you need to traverse a page table and insert things. They take a bit longer, but probably still within the sort of order of magnitude of an IPC. The thing that's potentially long running is capability destruction. Why? You have derived capability, so there's a derivation tree, and if you nuke the top one, the untyped, which is the original object, then all the derivations have to be cleaned up. And that's potentially a long-running operation. So this is the one really long-running operation that's virtually unbounded. It's only bounded by the amount of memory in the system, actually. So,
is that like a security issue? You could create a really deep trigger.
If you're not careful, it could be, because you could be leaking information by massaging capabilities. So yes, you need to be careful about how you do it. But in sort of typical cases, you don't really create and destroy capabilities a lot. Even if you sort of have a Linux system running in a virtual machine, that just runs with a fixed set of seL4 objects, right? It creates its own processes, but they are invisible to seL4. So it doesn't really manipulate seL4 kernel objects. So the long-running operations are mostly the destroy. And here is what we have sort of a half preemption kind of thing. They're called preemption points. They're not really preemption points because the kernel doesn't get preempted, but they're points where we check whether there's an interrupt pending. So the kernel is designed in what we call an incremental consistency paradigm. So you either have, we have kernel entry, and in between, and then do something, and then it's kernel exit, and of course the hardware disables interrupt on kernel entry, and the hardware enables interrupt on kernel exit, and we keep that this way for the whole execution. And if we have a short operation, so I call this an O of 1, so 1 being order of an IPC, then that's all we do. If there's a long operation, then we make sure we structure them as a sequence of short operations, where in between we check, after each of these short operations, we check is there an interrupt pending. And if an interrupt pending, we don't let it happen, but we exit the kernel and restart the operation. So basically exit and with returning to the same instruction. So it would just re-trigger the kernel entry again, but of course by doing the exit the interrupt gets enabled, so now the interrupt happens, the kernel gets entered again, but from fresh. There's no it's not a recursive or a nested exception, and then the operation gets restarted and we start from the beginning. So in order to make this work, we obviously want to make sure that there's progress. So these sub-operations need to satisfy certain conditions, and in particular they need to be restartable, they need to ensure progress, and they need to make sure that the kernel everything is in a consistent state, so we can't re-enter the kernel at this point. Now how do we do this? And of course if we do this, then we avoid having concurrency in the kernel. So how do we do this? Let's say we want to clean up an endpoint. So there's an endpoint and there's IPC operations pending on it, and we nuke the endpoint cap here, so the endpoint gets destroyed, and we have to clean up obviously any derived endpoint caps of this one, but also we have to abort all these pending IPCs. So what do we do? What's the sub-operation of this potentially long-running cleaning up the queue? Removing a single one, right? So This is easy to do. We have a linked list. We change the list pointer, take the first one out, and then we have a linked list again that's completely consistent, and we can, and this is the place where the operation can be restarted, and if we just repeat the same operation, we just keep on cleaning up. And of course, in order to avoid this queue growing in the meantime, we need to disable the endpoint capability in the first thing, right? That's the first thing we do, disable the endpoint capability. It becomes what's called a zombie capability, meaning it's still there, but it can't be used for an IPC operation anymore, so that ensures that the queue can no longer grow. And then we start cleaning up. As long as the queue is not empty, remove the head, and then do the check for pending interrupts. And if so, abort and restart, and otherwise continue. And so that meets all our requirements. We have a progress guarantee because we've taken one thing out and we've stopped the queue from growing again. And everything is in a consistent state. It's not different from a state that could have existed before the operation started. And by just redoing it, it will continue to clean up. It's a bit more difficult if you want to remove a batched capability. So rather than the endpoint capability itself, only the derived capability with a particular batch. And now you have the situation where on this endpoint, you could have many operations pending using different batches. So how do you clean this one up?
Go down the list, just remove the ones with the batch.
Okay. How can you be sure that this will terminate? Because say you want to clean up the orange batch. In the meantime, the blue thread can the blue threads can keep sending IPC, right? There can be more blue batches being queued.
How do you guarantee progress?
Yeah. In order to you can't always start from the beginning because you keep on going through the same blue ones, and you can't always go to the end because there could be a growing number of blue ones. So you need to keep track where you ended and where the queue originally ended. So there's 2 pointers that's needed, and so obviously first make the batch a zombie, point to the queue where you got preempted and where you started, and then you know next time you just start from this pointer and stop when you reach that pointer, and you're guaranteed both progress and termination. Not only termination, but finiteness. You have a bound. And the real challenge is you're deleting an object. Remember, the kernel doesn't have an heap. We can't just temporarily allocate a new object to store this information. It all has to fit into the capability you're trying to nuke. So that's a real challenge in encoding all this information, in particular the 2 pointers in just this one capability. But other than that, it's pretty straightforward. Whether the cap is a zombie or not. So it's marked as valid or not. And if it's invalid, then you know the rest doesn't contain capability information, it contains those 2 pointers. Good thinking. Any other questions?
Mark the end. So you need to mark the orange batch at the end of the queue. That is after the end of the queue.
So, okay, when I start the operation, I put this pointer where the end of queue is now. Right, and so as your colleague observed, you need a tail pointer for that, which we have. And then you start going through until you find an orange badge. You remove that, set the head pointer to that place, and then check whether there's a pending interrupt and you need to abort. Yesterday I had used real-time systems and what they need, etc. And we touched on real-time here because all this is what we do in order to make seL4 real-time capable. And also talked a little bit about what worst case execution time analysis is, or well, basically that you needed. And this is roughly how it is done. so this is a standard approach, and we applied this one to seL4 a while ago. So the idea is you obviously have to do the worst case execution time analysis in the binary. Some people do it on the source code. Of course, they're kidding themselves. It's ridiculous. And what happens is from the binary, you extract the control flow graph. So that identifies basically path through the program. Right? And then there's an analysis tool that takes a control flow graph and turns it into a integer linear problem, and there are standard solvers you can throw in this, and that basically identifies longest path through the graph. But the point is, of course, just because a particular path has the most instructions to go through doesn't mean this is the longest execution time. You need more for that. So this is where a microarchitecture model comes in. So that basically depends on the amount of sophistication you have, may model the pipeline if you want to have a really tight analysis. So that gives you information on how a instruction progresses through the pipeline, for example, whether it can get stalled by a data dependency with an output register or an input register. And the other thing, of course, you need is loop bounds. Because if you don't have any loop bounds and there is while loops in there, then obviously the path is infinite. So you can't conduct, if you have programmatically not bounded loops in there, then you need to somehow inject the worst case bounds of those loops in order to do get any finite execution time bound. When the IOP solver spits out a candidate path, many of these tend to be infeasible, meaning they depend on mutually exclusive preconditions. So you have an if branch on a certain condition taken, and further down an if branch on the same condition not taken. That's obviously an infeasible path. And the idea is, of course, this will always only give you a safe bound on the execution time, but you want to get the bound as tight as possible to make the whole result usable in practice. So you need to eliminate these infeasible paths, and that means basically going through the preconditions, checking, basically building for each of these paths a big Boolean product of all the preconditions and see whether the result is provably false or not, and if it's false, then you can throw away that path. The typical analysis tool only does the upper part of this graph, and these things are fed in externally. And they are obviously where you can get a large amount of pessimism. If your loop bound test is fairly is not tight, then you may overestimate the loop bounds here. If your infeasible path analysis is not complete, you get a pessimistic worst case execution time because it does include infeasible path. And of course, depending on how sophisticated the architecture model is, you get more or less pessimistic results. In the worst case, you ignore pipelining and you just use the worst case latency of every instruction, and of course that typically gives you a result that's about an order of magnitude too big. If you always assume every cache access is a miss with a dirty line to be replaced, then you may get 2 orders of magnitude pessimism. So this is what really makes the whole thing tricky. And when my student did this a few years ago with seL4, first he found out none of this scaled to something as small as seL4, just 10,000 lines of code. The real-time community likes to play with toys, 100 lines of code or something like that. And so he had to do a lot of work just to make the stuff scale on the kernel. But then there was actually no tool with an architecture model for a protected mode ARM processor, so he had to basically steal that from some simulator and make sure that's all sound. Basically, you only overestimate and never underestimate latencies. The tool had a cache analyzer, so it did an analysis of latency of residency of data in the cache and could eliminate a lot of potential cache misses by proving that things had to be in the cache, and of course that gives you a much better bound. He did, however, still do a offline analysis of the infeasible path and the loop bounds, and then the next step is he threw some static, some SMT solvers or whatever at both of these problems and eliminated a number of the infeasible path and proved some loop bounds. But it turns out that was incomplete, and he could only prove bounds automatically on about half of the loops in the kernel. I think there's about 20 in there, and about half he could automatically prove bounds, and the others he had to do by manual reasoning, which is of course error prone. Can you imagine what the problem is with determining these loop bounds? Why can he determine the loop bounds by manual inspection, but in this framework not automatically? Hey?
It's like equivalent to solving the whole thing.
So in a very general sense, yes, all this is equivalent to the whole thing. But we generally have a well-behaved thing, right? We know the kernel never iterates on an unbounded loop. It's all bounded by something. In the worst case, loops may be bounded by the amount of memory in the system, which is not too good, right? And when he actually did the first analysis, that's basically what he found. There was some bounds, some loops that were only bound by the amount of memory in the system. And this is basically the capability destruction problem, right? If you have a capability that can be arbitrarily delegated, then, well, every page of untyped memory could have been retyped into a capability of that sort, and they could be nested, etc. So, and as a consequence, the worst case execution time he came up with was in the seconds. And he could actually construct that example and run it, and it took seconds. So this is obviously not the way to go. And this is when he then started optimizing these preemption points and really analyzed the kernel, where these long operations and how to split them up. The other problem, of course, is when you do the manual inspection, you do it on the source code, of course, where you have a lot of information. This thing operates on the binary, and you lose a lot of semantics by the translation process. And in particular, one big problem is pointer aliasing. To prove that two separate pointers don't refer to the same object. And you need those for both the infeasible path analysis as well as the loop bounds. And you don't get that from the binary. Whereas from the source code, it's usually easy to establish. And as a matter of fact, seL4 is designed so there's no aliasing of certain pointers, etc. But the analysis running on the binary doesn't know that. What then another student did was actually, and I'll talk about this later, importing some of the stuff we had proved about the source code into the worst case execution time analysis. So basically linking the binary in a provably correct way to the source code, and being able to use invariants that have been proven at the source on the binary level and feed them into this analysis, and that made the whole thing sound and really bulletproof, more or less. And this is what we found. So these are microseconds, and the computed bound on the worst case execution time latency, this is on an old ARM11 processor, a relatively slow processor, was about 400 microseconds. And by analyzing these longest path which the analysis gives you, you can actually reproduce these cases, right? And he did that and could actually measure 100 microseconds. So there's a factor of almost 4 in potential pessimism. Of course, we don't know where the worst case execution, the worst case really is. It could be close to here, could be close to there. We have strong reasons to think it's actually close to here. And the reason there is that this processor has its cache replacement is random. And random basically you mean you have to model this as a direct map cache where you get, whenever you have a conflict, a potential conflict, it's an actual conflict and we replace it. And this means that almost certainly the actual worst case is relatively close to here, and the pessimism comes from the underspecified cache. But of course there's no proof of that. But it's actually not too bad. So factor 4 pessimism, of which at least half is due to underspecified hardware, isn't too bad. Unfortunately, we can't do this on any recent processors anymore, because as soon as ARM started to produce out-of-order processors, they stopped publishing any of these latencies, even for the in-order processors, and we're stuffed. Fortunately, there's RISC-V now, and with open implementations, and with a RISC-V implementation, we can actually analyze the actual implementations and build the pipeline model from that one, ideally automatically, so we will be able to do a really sound worst-case execution time analysis on RISC-V again. So 400 microseconds sounds a lot. But remember what I told you yesterday about actual deadlines in real-world hard real-time systems. What was their order of magnitude? They were typically in the milliseconds, up to seconds, right? So 1 to 100 milliseconds is a typical range. So that basically means, okay, this is a bit uncomfortably close, but it's not too bad. And I'm fairly convinced, maybe 10 microseconds is a bit optimistic, but I'm pretty sure we could get it down to 20 microseconds. The problem is it would require much more work on the kernel in optimizing these preemption points, etc. And at the moment, since we can't do it for any recent processor anyway, there's not a lot of motivation to do that. We'll probably get back to that pretty soon as once RISC-V hardware becomes more widely available and we're using it. So this was one other aspect of real-time support in seL4. And the other one is really coming back to the various issues of, oh, not quite there yet. There's a few scheduler optimizations. There have been long-standing properties of L4 kernels. And one of them is called lazy scheduling. So the idea is, what the microkernel mostly does is sending IPC for and back, right? And so that means, okay, you have a server that's blocked, you have a client coming along, it sends a request to the server, that blocks the client, the server picks up the request, processes for a while, replies back to the client, which blocks the server, client receives the message, gets unblocked. So on every IPC, you block and unblock a thread. So that's a lot of queue manipulations and all these cost. And of course, as soon as you've done it, you undo it, right? You block the client, put it in a waiting queue, and then the server executes for a few milliseconds, and then you get back and unblock the client again. So in a tight loop, you do a lot of block inserting and dequeuing the same threads over and over again. So that's pretty wasted. So the idea is, okay, let's do this lazily. Instead of taking block threads out of the ready queues, just leave it there, and next time the scheduler goes through it, cleans it up. So this is then how the scheduler roughly looks like. It goes through the list of priorities, top down, looks at every priority level, looks at the list of queued threads, check whether the thread is runnable. If so, that's the one we want to schedule. Otherwise, dequeue it and keep on iterating. This is how L4 kernels have been built for a long time. What could possibly go wrong? Any thread in the system could possibly be one of these blocked ones. As a matter of fact, all but one is typically blocked, right, on a single core. So there's a lot of blocked threads, and they could all be in the ready queue. So the cost of a schedule operation is order of threads in the system. That's really bad, right? That could be a long time. So basically, yes, we have an unbounded, worst case, unbounded scheduler operation. Average case, it's sort of okay. It's not great because you still have to do a lot of work. Typically, you have to clean up a fair bit, but probably only a handful or so. But the worst case is really bad. So this is not the way to do real time. Is there a way to do it better without losing performance? So the laziness here, the thing that makes it fast is don't dequeue blocked threads. Leave them in the ready queue. How about turn this around? Don't enqueue unblocked thread. Don't put them in the ready queue. Because if you think about it, there's only ever one of those, right? There's only one thread that's runnable but might be in a blocked queue, and that's the presently executing one. So the invariant is then the only fix-up you need to do is when a time slice preemption happens, the presently thread is now waiting queue potentially, but it's actually ready. So at that stage, you have to insert it in the ready queue, and that's the only cleanup you have to do. And the actual scheduler looks then a bit different. We still need to run down the list of priorities, but then you don't need to process anything more in the queue because you know anything that's in the queue is actually runnable. So you would just pick the first one, and we only have a singly nested loop, and it's bounded by the number of priorities. And of course, there's a standard optimization by using a bitmap to tell you which is the highest priority that's actually has threads in there, and that makes it an O of 1 operation, even worst case. And student who came up with this was my student Benno, and that's why we call it Benno scheduling. And so we only need one fix up. The cost of fixing this up is one queue operation at preemption time, and otherwise it's all good and fast. So we do have a O of 1 scheduler, but still avoid doing these queue operations during IPC. So that's the important point. And a related optimization that's always also been with L4 from the beginning is what we call direct process switch. Remember when I looked at the fast path last hour of where we do the context switch without actually invoking the scheduler and just running on the sender's time slice. So this is what's called the direct process switch, where we say, okay, we don't need a scheduler because we know typically that the receiver is to be continued. Remember, an IPC typically is client contacting a server. In a well-defined system, the server should run at higher priority. So that's easy to check whether it's actually the case, but normally the receiver will be higher priority, so you know because presently you're the highest priority running thread, you're switching to a higher priority thread, you don't need a scheduler to do that, you can just execute. On the switch back, typically if it's a call type operation, you also know that now the high priority thread is blocked. All you need to know is whether anything of higher priority than the original sender has been unblocked in the meantime. And again, that's an easy check. Just check what's the highest ready process priority in the system, and if that's the one you're switching to, then you can continue without invoking the scheduler. So this is the direct process switch, and it implies that we have a time slice donation. Now, what could possibly go wrong with time slice donation? Again, think real time. What does it have to do with deadlines?
Donating your time slice deadline is extended or not. It's going to happen later on, right?
So what do you need to know in order to ensure that everything meets its deadlines? You can't really do that. You can't reason about timeliness in a system if you don't account for time properly. You need to know who's consuming which time so you can ensure that the important things meet their deadline. This destroys that completely, right? You lose accountability of time. And that was a bad issue in in L4 kernels for a long time. So in particular, it hits this case of delegation. So yesterday I said that a good way to implement critical sections in real-time systems is by delegating, meaning putting the critical section into a server that's contacted by IPC that automatically guarantees mutual exclusion because the server is single-threaded and can only operate on behalf of one particular client at a time. So this immediately gives you nice locking properties. By running the server at the ceiling priority, you automatically get priority ceiling protocol implementation for free. It's all very easy. Except, of course, this time slice donations thing messes it up completely because now the server executes with a donated time slice of the client. What happens when the time slice exhausts while the server is executing? Well, the server gets its new time slice at its priority, which is the ceiling priority, and now it replies back to the client, and the client operates on the server's time slice at a higher priority than it should have, and it screws all your priorities and everything in the system. So you have non-observance of priority, real priority violations, and you have incorrect accounting of time. In particular, if this client gives itself a really short time slice, it can sort of keep on operating on the server's time slice without ever consuming time and basically call the server in a tight loop and starve another client that's behaving correctly. So that's really, really bad for real time. So how do we fix this? Obviously, this way of time slice donation that, okay, the receiver executes on whatever happens to be left of the sender's time slice is a bad idea, right? It's an unprincipled way of optimizing this IPC that really costs you in terms of having any predictability in real time. So we needed a model for the proper and principled treatment of time in the seL4 kernel, and that is our MCS model. One of the nice properties it has, it ties time into the capability model. So for the first time we now have caps for time, and it's actually the first system, together with some concurrent work at George Washington University, that has a real-time capable model where time is represented by capabilities. Seems like it should be straightforward, but it's actually a hard problem. So the idea is the classical model, a thread has two scheduling parameters. The one is the priority and the other is the time slice. In the new model, we have a generalization of a time slice called scheduling context. And a scheduling context is basically a right to use time on the processor. And it's, as everything in a decent system, protected by capability. So in order to have a thread that's able to run, you need to give it a capability to a scheduling context. And a scheduling context is a first-class kernel object like thread control blocks and endpoints, etc. And it contains a number of metadata, but the most important ones are a period and a budget. And what this scheduling context says is if a thread is drawing its right to use the CPU from the scheduling context, then in every t amount of time, it's allowed to use up to c of CPU time, where c is less than or equal to t. And if c is equal to t, you get the behavior of the present L4 kernel, so it emulates that faithfully. But in general, you can restrict the amount of time a process draws from the processor. And this is the basic time protection mechanism we need, for example, for doing mixed criticality. So we can now limit access to CPU time, and this is an example. You can have a scheduling context that says you're allowed to use 2 units out of every 3. And you can have a separate scheduling context that says you're allowed to use 250 units out of every 1,000. In particular, this would be the higher rate monotonic priority. This would run at low priority, but this couldn't staff that one because it's forced to leave 1/3 of the time over, which is enough for this one to run. So this way we can support the requirements of mixed criticality systems without having to trust everything in the system. Remember the example I gave yesterday was low rate control loop, which is the critical thing, together with the high rate network driver. So this would be a good example for network driver. For example, every 3 microseconds, it's allowed to use up to 2 microseconds. This is very generous, actually. But we still have for every milliseconds, okay, you probably have a bigger value there, but you get the image, right? We can guarantee enough time for the critical control loop to execute. How does delegation now work with scheduling context? We have a new notion of what's called a passive server. So you can have threads that have a scheduling context, and that makes them runnable. And we can have threads that don't have a scheduling context. That means on their own they're not runnable, but they can run on a donated scheduling context, and the donation happens by IPC. So this is now a really principal way of doing time slice donation, where it's well defined what happens. The client invokes the scheduler, it passes its scheduling context along, the server, the client invokes the server, not the scheduler, the server executes on the client's scheduling context, and when it replies back, then the scheduling context reverts back to the client, and in the meantime, the time consumed by the server has been charged to the client scheduling context, so our accounting is accurate. What could possibly go wrong? So interestingly, L4 always had a notion of threads as active entities, and you send messages between threads. This now gives what's called optionally a migrating thread model, because logically it's actually the thread migrating into this protection domain and executing there and coming back, right? And in terms of how you would implement a migrating thread model, it's pretty much that, because if you want to have migrating threads, you need to have a stack waiting on the other side to execute the code. So it really is what a migrating thread model looks like. And they have certain advantages, and basically you can now choose. You can have an active server or a passive server in the once you get the migrating threads, and otherwise the old model. Okay, but what could possibly go wrong with this model here? Exactly. What happens when the scheduler when the budget runs out while the server is executing? Then we sort of have a problem, right? So this comes back to what we need for mixed criticality support. We need temporal isolation, which scheduling contexts give you. But you also need a way to safely share resources. And from what I told you so far, we don't have that yet. We can share these resources, but not safely, because if one of these clients, so this is the example I had yesterday, where we have a shared resource and we have different criticality threads accessing that resource. The example I gave, the critical control loop and the communications module that updates the waypoints, and the waypoints are the critical data in the shared server. So the server is shared across criticalities. And so the problem is, yes, the client, while the server is executing on behalf of the low criticality client, it runs out of budget. What happens? We block the high critical client, and of course that's really bad. This would now block until the scheduling context is replenished next period of the client, which may be a long timeout, and the highly critical thread may miss its deadline. So what do we do? What's the natural L4 model for doing this? So the characteristic of seL4 or any L4 kernels is high performance and policy freedom. So we're looking for a policy-free mechanism for dealing with this situation. Scheduling contexts are policy-free mechanisms for doing timing correctly, time accounting correctly. And so the policy-free mechanism for dealing with this situation is raise an exception. So at the moment, seL4 has 2 kinds of exceptions. It's got page faults and it got other exceptions. So we introduce a third one, which is timeout exceptions. And so you can, with every scheduling context, now it's a thread property, that when it overruns its budget, then a timeout exception is optionally raised, and that goes to an exception handler. And then that implements the actual policy of how to deal with the situation. And there's basically 3 or 4 ways you can deal with this. One is it can eject a emergency budget into the server. So that's one way to deal with it. The other is it can roll back the server and restart, dump this IPC. Basically, the client did something it shouldn't have done, which is invoke the server with insufficient time left. So it's his problem if it loses. So we just roll back the server and abort the IPC and let the next client operate. So obviously this requires puts certain obligations on the server. It's got to be either stateless or it has to implement a transaction-like model that can be reset, which in many cases is very straightforward to do. And obviously the client has been misbehaving. You made the put down its priority. Remember, the client may be this Ethernet driver. No, you've been a real baddie, and we'll run you at lower priority and keep you out of keep the rest of the system out of trouble. Or we could even implement priority inheritance if you really want to, which I think is probably not what you want to, but basically this is how it works. So we now have the mechanisms for dealing with time properly in seL4. And finally this issue, last remaining serious issue of L4 kernels of unprincipled time management is finally done. So now we're at the end. I gave you sort of a number of issues we had to deal with over the years in trying to really come up with the right API for a microkernel, and I think we got pretty close. And some of the learnings here is, how does seL4 compare to the original L4 kernel? And I told you there are 2 papers, 93 and 95, where Jochen described implementation tricks and design decisions in L4, which he claimed were needed to make it really fast and flexible and everything. And so it's a long list, 2, 4, 6, 8, 10 to about 2,000 things. And if we look at what's left of that in seL4, turns out, well, we actually threw a lot of this stuff out. And most of these things, including some which were really very dear to Jochen's heart, have been dumped. A few others we have changed. For example, lazy scheduling, as I said, we converted that into Benno scheduling to make it suitable for real-time systems. The direct process switch was changed from this undisciplined time slice donation to the really principled scheduling context donation. Zero copy register messages are nowhere near important as they once were. But we kept a few core characteristics. One is the kernel is still non-preemptible to make sure it's blindingly fast, but we've done it in a way that still allows us to do hard real-time. We kept synchronous IPC, although the semantics have changed a lot, and it's really morphed from a general message passing mechanism to just the user-controlled context switch, really the remote function invocation. And so arguably you should color that one pink. We still have user mode page fault handlers. This is very core to the any real microkernel has that. If it doesn't, then it's not a microkernel. Same with device driver, right? Device drivers do not belong into a kernel at all. Certainly not a microkernel. They shouldn't really mostly be in the Linux kernel. I mean, it's insane that Linux has USB stacks and audio drivers and all that shit in the kernel. I mean, that's just a disaster waiting to happen. And it does, obviously, all the time. So they can sort of, those changes we did can be sort of categorized in one of 2 major shortcomings. The one was the kernel had no real resource control. And we fundamentally fixed that in seL4 by the combination of having capability-based access control and this model of exporting resource controlled completely to user level, which with scheduling context we now extended to time. And it just had a completely over-optimized IPC abstraction that was trying to do too much. And we disentangled that by throwing some stuff out. Synchronization, we now have notifications for that. Memory management is done differently, and scheduling is done differently. And what remains is the principles on which seL4 actually has been built. So fully delegatable access control, which we get from the capability system, exporting all resource management to user level, and this is a really key way of making the kernel policy free, but also for enabling strong isolation. We did this without sacrificing performance. This was very close to my heart. When we started the seL4 project, I told the team, I will not consider this a success if we lose more than 10% in IPC performance. And when we published the first paper 10 years ago, we were right at the 10% border. By now, seL4 is faster than any kernel we've built before. So my motto that security is no excuse for bad performance, we're totally true to. We wanted it to be suitable for hard real-time use, because we're aiming it, among others, at safety-critical systems like avionics, etc. And so this is what got us this approach of the incremental consistency paradigm, and now finally fixing up time management properly. And then this was the main thing. seL4 was designed from the beginning to be provably correct. And this was completely revolutionary in a sense that people have been trying that for 30 years. So this is the first paper that talks about verifying an operating system. And the paragraph here says, our research seeks to develop means by which an operating system can be shown data secure, meaning that direct access to data must be possible only if recorded protection policy permits it. So basically, they wanted to prove that the system enforces security. And this was done in 1980, almost 40 years ago, and they didn't get there. They tried with a really stripped down Unix system, and the whole project basically, by the time ended, they had managed to specify part of the functionality, but they never proved anything about it. And it wasn't until 2009 that we finally did that with seL4, and I'll talk about that in week 9, I believe.